Hey, what's up, guys? This is Sheng here. So this time, 1,774 closest dessert cost. So for this one, you would like to make a dessert and are preparing to buy some ingredients. So you have n ice creams, uh, base flavors, and you have m types of toppings to choose from. And so to make an ice cream, you need to use exactly one ice cream base, and then you can add any number of typings you want from 0 to more. Okay, and there are like at most 2 of each typings. So and you're given like some inputs. Basically, you have 3 inputs. So the first one is the base cost, right? So basically it tells you each cost for each base flavor, and then the cost for each of the toppings, and then target. And your task is to find the closest possible cost of a dessert to a target. And if there are multiple ones, basically if the difference is the same, we need to return the lower one. Basically, who has a smaller total cost will be the ones we want to return, right? So that's why we have. So for example, we have 1734. So target is 10, and in this case, we can get exactly 10, right? That's how we just return 10 here. And here's another examples here. We have target 17 is 18. We have 17 here. We need to return 17. And this one, example 3 here. So here is give us like a example like where we have 2 costs that can give us the same difference, which is 8 and 10 here. So both of them will have the difference equals to 1, right? But in this case, we want to return 8 because 8 is smaller than 10, right? And for this one, we have 10. Yeah, because basically we only have one base, right? And since we need at least one base, right? That's why we have 10 here. So and the constraints n and m is pretty small, which is 10, right? So which means that for this kind of problem, we can most likely do a brute force, right? So we can simply try all the possible ways to make an ice cream. And among all of them, we just maintain the biggest, sorry, the target, right? We maintain the best target we can get, and that's it, right? So I mean, to try to enumerate all the possible uh, combinations of ice cream and the toppings, I think there could be multiple ways, but for me, I just do this. Basically, I have an answer equals to 0, equals to the system dot max size. Okay, and so for me, I just do a base, right? So I enumerate the base first because we need the base at regardless, right? Then for each of the base, given given the current base, I just try all the possible toppings scenario. Okay, so basically I'll do a DFS of zeros. I'm going to create like a DFS method. So I'm gonna have like 2 parameters. So the first one is topping index, right? And the current one is the current cost. So that's how I enumerate all the possible toppings, right? And at the beginning, since we need a base regardless, that's why the initial cost for this current DFS is going to be the base, right? And yeah, so basically every time when we have like a cost here, right, we want to maintain that, right? We want to check if this cost can give us a better answer. So which means that if, right, I'm going to do this basically. So the if ABS of the current cost minus target, right, is smaller than the since we're using this answer to store the our best best cost, right? And ABS of the answer minus target, right? If that's the case, right, we want to basically update the answer or what? So this is the smaller case. There's another case which is the a tie, right? So for the tie case, or if this thing is the same, right? And the current cost is smaller than the target, then we also want to update the answer. So we have the answer equals to the current cost, right? Because since here I'm only using one variables to maintain that. You can also have like another difference variables to help you calculate this one. But I think this one one variable will be enough. Yeah, so I think that's that. And we can also have like some early terminations here. For example, if the current cost equals the target, right? And then obviously, I think actually we can put this one on the very top here. Basically, if the current one is the same as target, we know, okay, we find the best answer already, right? So it's going to be a current cost, and then we can simply return from here, right? But I think this one is not mandatory, because I think this one will also take care of that. It's just here, it's just like early termination to help us to make this program run a little bit faster, right? So early termination, right? Termination. And another one is like this. Basically, the so after the current one, I mean, if after calculating the answer here, if the current cost is greater than target, right? So we also return, because if the current one is already greater than the target, there's no point to continue adding adding the toppings on it, because the difference will become bigger and bigger since we are going to get the closest one, right? No need to add more toppings, right? And then up here we try to add toppings, right? So how do we try that? Since we can add either 0 or more toppings, right? And for each of the toppings, we have like we have at most two toppings we can add, right? So which means that I'm going to have like a for loop here in range of 3. So this one basically I'm looping through the toppings, right? For the current topping index, right? I'm trying to add either 0 or 1 or 2 toppings on top of for the current index. Basically that's why I have DFS of topping index plus 1, right? And then I have so I have current cost, right? Plus what? Plus the topping cost of the topping index times I. So this is how I basically, so this for loop can give us all the possible combinations of the toppings, right? Because for the current toppings here, so when I equals to 0, it means that we're not adding current toppings, right? Or we're adding like one one top or one count for the current toppings, or we add 2, right? And then after that, we try the next toppings, right? For the next toppings, we also try add 0, add 1, or add 2, so on and so forth. Okay. And Yeah, so I guess, okay, so for the non-local, okay, to update the answers, I'm going to have non-local here, answer here. So, I mean, here, I simply return the answer in the end. I think this should work if I run the code. Index out of, oh, yeah. So we also need to add another like termination point here. Basically, whenever if the topping index equals to the length of toppings, right? Sorry. Otherwise, we have like a index out of range arrow here. We also return here. Okay. And the reason we added here below here instead of at the beginning is because after basically after consuming the current let's say if after consuming the last toppings here, if we break at the very beginning, will not basically process that last toppings result, right? Because our check logic is here. That's why we have to always for each of the costs here, we always want to process the cost first before doing any of the return here. Okay, cool. So if I run the code, accept it, right? Yeah, there you go, right? So basically, we simply try all the possible scenarios here. For each of the scenario here, we have, I mean, the time complexity. I mean so we have like n here. Let's say n is the 10 here. So for each of the n here, we have what? We have for loop here, right? So we have 3 here. We have 3 different scenario here, and basically it's going to be a 3 to the power of 10, right? Because for each of the scenarios here, we're gonna have 3 scenarios here, and for each of the one, we also have 3. Basically 3 times 3 times 3. And then we have another 10, basically. I think this is the time complexity for that. Yeah. Cool. So, I mean, that's it, right? So for this one, since there's no better or greedy solutions to solve this problem, and also given this kind of small constraints here, right? We'll just basically try all the possible combinations to make a dessert, right? So first we try each of the base, and for each of the base, we use the DFS to try all the topping scenarios. And for each of the costs, we're gonna calculate the final result, right? And then we have some like early termination here. I think I can remove this one. This should also work. Yeah. Basically, this one is not necessary, right? I'm just simply add it here, but it will not affect our final answer. And here's like the main logic to try all the possible toppings from 0 to 2, right? And we do this for each of the toppings. Yep, I think that's pretty much I want to talk about for this problem. And yeah, again, thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.